Hello viewers, question 4, and we now move on to finding the equilibrant of a force system. So previously we have been looking at the resultant, which is when we combine several vectors, what would the single vector be that would have the same effect. Now we're looking at the equilibrant, which means we're looking at adding in an extra vector that makes the resultant 0. So this extra vector would need to cancel out any resultant that from the existing vectors. It therefore needs to point in exactly the opposite direction, and it needs to have the same length. So that gives us a way of finding the equilibrant. We first strive to find the resultant and reverse the direction. For question 1, we were talking about finding the analogy of displacement. So if you pace out a certain distance in a given direction for the first vector, and then change direction for the second vector and pace out its length and walk in its direction, and do the same for all of the remaining vectors, the overall displacement, the resultant would be where you end up relative to the starting point, how far away and in which direction. The equilibrant would therefore be what you need to do, the vector that takes you back to the starting point. Okay, so we're going to strive to find the resultant of this force system. So we'll draw the force table, and then at the end we'll reverse the direction to get the equilibrant. So let's do our force table. So we've got 4 forces here. Let's start with the upwards 6 kilonewton force, and let's work out its horizontal component and its vertical component. So the horizontal component is 0 because it is a vertical force and it's pointing upwards, so therefore the vertical component is positive, and it is positive 6. Working our way to around clockwise, so on the right we've got a 6 kilonewton force at 30 degrees below the horizontal. So its horizontal component is going to be positive because it's pointing to the right. Its hypotenuse is 6, and we're looking for the adjacent, so it's going to be the cosine side. So it's 6 times cosine of 30, and the vertical component is going to be vertical is opposite, and we know the hypotenuse is 6, which means we are looking at the sine side. So this is going to be 6 times sine of 30, but this is below the horizontal, it's pointing downwards, so the vertical component is negative. Working our way around clockwise to the other 6 kilonewton force, which is pointing to the left below the horizontal, we have a horizontal component of the same. It's going to be the hypotenuse is 6, horizontal component is the adjacent side of our right triangle, but this one is pointing to the left, which makes the horizontal component negative. And in the vertical direction, the vertical component is the side opposite our angle. We know the hypotenuse, so this will be also 6 sine of 30, and as it's pointing downwards, this will be negative. Now we have a single 11 newton force, but we need to be consistent in our units, so let's convert that into kilonewtons by dividing by 1,000. So that becomes 0.011 kilonewtons, and that is our leftwards force. So we've got 0.011 kilonewtons, exactly horizontal, which means the vertical component is going to be 0, and the horizontal component is negative 0.011. It's pointing to the left. So we can now find our totals. So we've got 0 plus 6 times cosine 30 minus 6 times cosine 30. Those two are going to cancel out, leaving a total of negative 0.011. And in the vertical component we've got 6 minus 6 times sine of 30 minus 6 times sine of 30, which gives you 0. So let's do our rough direction. Actually, because the vertical component of the resultant is 0, there's only a non-zero horizontal component. Our rough direction isn't going to be so rough. It's going to be exact because it must be pointing horizontally, which means we won't need to use Pythagoras and we won't need to find the angle here. So your resultant is equal to negative 0.011 kilonewtons, and if we reverse the direction we get the equilibrant would be positive 0.011 kilonewtons. In other words, the equilibrant here would be an 11 Newton force pointing to the right. Now what's interesting about this question is that the resultant turned out to be just a 0.011 kilonewton force. In other words, the 6 kilonewton force, the three of them, the three 6 kilonewton forces exactly cancelled each other out. So let's have a look at a vector diagram of why that is. So we have a 6 kilonewton force pointing upwards, and let's have a look now at the one that was pointing to the left, downwards. So we had, from there we had a 30-degree angle. This is a 6 kilonewton force, 30-degree angle below the horizontal, which if this is 90 degrees because that's vertical, and this dotted line here is supposed to be horizontal, so they are 90 degrees apart. If that's a 30-degree angle, then this must be a 60-degree angle inside there. Now let's draw in another little dotted line at the end of that first 6 kilonewton force, and let's draw in the other 6 kilonewton force. So this angle here, if we look at this top triangle, there we would have a 90-degree angle. This is a 60-degree angle, which makes that a 30-degree angle, and this force here, the one that was pointing downwards rightwards, was pointing 30 degrees below the horizontal. So we've got two 30-degree angles here. That means that that angle must be 60 degrees, and since the total angles in a triangle must add up to 180, the third one must also be 60 degrees. So if we draw a vector diagram, the three 6 kilonewton forces here make an equilateral triangle. They make a closed shape, which means they exactly cancel each other out, leaving just the 11 Newton force, and therefore all that the equilibrant needs to do is cancel out that 11 Newton force by being an 11 Newton force in the opposite direction. Okay, thanks for watching. Over and out.